Having discussed thermal detectors in the last lecture, I will now go over to a discussion of various types of quantum detectors. These are the ones that are extremely important for remote sensing, for fiber optic communication, for all types of detection of very fast and very weak signals. These quantum detectors have the advantage of very high sensitivity or high detectivity, high D star values, almost reaching the ideal value of D star predicted from theory. They also have very fast response. That's one of the advantages, down to tens of picoseconds. However, they have some disadvantages, that in the sense that they are often confined to a limited region of the spectrum, limited spectral response, depending upon the band gap of a semiconductor, for example. They often require low temperature operation for high sensitivity. That means it adds to the cost, it adds to the size, it adds to the power requirements if you have a thermoelectric cooler. Low temperature operation means usually 77 to 100 K, but for very high sensitivity, sometimes you require operation at 4K. They're also relatively expensive, and in some cases they require not only temperature control, but they need controlled power supplies, highly stable power supplies, because the operation is sensitive, depends upon the applied voltage. So, if we compare different types of thermal quantum detectors, as we've seen before, they can be classified into broadly photoemissive, based on the external photoelectric effect. That means the ejection of electrons from a solid into vacuum. So these are basically vacuum devices. We have photoconductive, photovoltaic of various varieties, and one can say that the new generation depends upon quantum wells, quips, which also depend upon phenomena like photoemission and photoconduction, but they have a slightly special principle of operation. So we'll take up these devices one after the other. Broadly, we can make a comparison between the different types as follows. We can compare their gain, response time, and operation temperature. Say for photoconductive, which is called PC for short, we'll show that the gain can be from 1 to fairly high, in special cases 10 to the power 6. The response time is not all that fast, 10 to the power minus 3 to 10 to the power minus 8 seconds. And the operating temperature could be from 4.2, that's liquid helium temperature, to 300 K. PN junctions are the simple type of photovoltaic detectors. We have no gain. Response time can be very fast, 10 to the power minus 11, and they operate at 300K. A special type of PN junctions are PIN, which I'll discuss in somewhat greater detail later. PIN diodes, they have no gain of only unity, slightly slower than PN junctions because of the I region, 10 to the power minus 8 to minus 10, and they also operate at 300. Then we have metal semiconductor detectors, or metals Schottky barrier type of detectors. They are the fastest. They can go down to 10 to the power minus 12 picosecond scale, and so for detection of very fast laser pulses, metal semiconductor diodes are the ones that are used. Avalanche photodiodes, they're also basically, these are all subclass of photovoltaic. They can have gain of 10 to the power 2 to 10 to the power 4 due to impact ionization and avalanche multiplication. Speed 10 to the power minus 10, operating temperature. And we can have phototransistors, bipolar transistors, which can exhibit gain. Speed is rather limited, 10 to the power minus 8 compared with the others. Room temperature operation, and then we can have photo FETs, 10 to the power 2. These are the sort of maximum gains available. They are slightly slower, as you know. If FETs are slightly slower than bipolar devices, 10 to the power minus 7, and operating room temperature. So, depending upon your requirements, one can choose any of these particular types of detectors and get the best operation possible. Let's take up the photoemissive detectors first. Photoemission depends upon the phenomena of a photon coming in. If it's a metal, electrons at the Fermi level can be excited, and if they can overcome the work function, the electrons are emitted into vacuum. And for example, if there is a electrode here which is at positive charge, they'll be collected. Typically, a device will have electrode, and this is a photocathode in which the light is incident, and obviously H nu must be greater than phi. So it's a vacuum device because the electrons have to be collected by the anode. However, the photocathode itself is a solid state material. Typically, the work functions of most materials vary from 3 to 5 electron volts. Okay, so as a result, these devices, photoemissive devices, are only can only function in the blue or the, because if you remember the relation lambda is 1.2 by h nu, 1.24, and this is 3 eV, this comes to about 0.4 microns. Okay, so typical photoemissive devices which have such large work functions will only work at lambda less than equal to 0.4 microns. That's in the blue on the UV. Okay, so this was the state of the art when in the 1910s and 20s, when there were metals, typically tungsten, molybdenum, etc., were used. Of course, the working of this device is based on the photoelectric effect as described by Einstein. The energy of the kinetic energy of the electron is obviously equal to h nu minus phi. Okay. There's a cutoff at the value h nu is equal to phi. So from the material point of view, if you want operation in the blue or in the visible range, obviously you have to lower the work functions, and it found that material like cesium has a work function of only 1.9 electron volts. However, cesium is an alkali metal. It's not all that stable. It oxidizes very easily. But if you have a work function of 1.9, then obviously lambda cutoff will be 1.2 by 1.9. So something 0.62 microns. Okay, so you're in the visible. So this can operate in the visible, but not in the infrared. So there was a lot of effort in trying to develop the first type of photocathodes that were developed were typically photocathodes which had cesium coating. Okay. Okay. And these had efficiencies of about 0.50 at 0.8 microns. Then there was obviously cesium is important because of this low work function, alkali metal. This is called an S1 type of photocathode. This is S17 cathode. This is efficiency of about 30% at 0.50 microns. Then we had things called multi-alkali cathodes, Na2, Sb, Cs, so S20. Efficiencies are about 40% at 0.4 microns. Okay, as you see that these are not going into the infrared. They're all cutting off in the visible. These were all developed rather empirically and were widely used in the 50s. In the early 60s, people started looking at what happens if you take a semiconductor such as gallium arsenide and coat it with cesium. And thereafter, a whole series of new materials were developed, such as indium arsenide, phosphide coated with cesium or cesium oxide, gallium arsenide, and timonide coated with cesium oxide. And the remarkable fact was these could give efficiencies of about of the order of this could give an efficiency of 35% at 0.4 microns, but we could push the long wavelength limit to something like indium arsenide phosphide 0.8 at 1.08 microns, or 0.27 at 1.06 microns. So the long wavelength limit could be pushed into the infrared. This came about through detailed understanding of the properties of semiconductor surfaces. And so if we look at the band diagram at a semiconductor surface, if this is the vacuum level, in a semiconductor which is not degenerate, the Fermi level is somewhere in the middle of the band gap. If this is EC, this is EV, then we know that difference between vacuum level and EC is chi. Difference between EF and the vacuum level is phi. And if photoemission experiments are done on a semiconductor, question was, what is the threshold energy? What is the threshold energy for emission? If you take an intrinsic semiconductor, such as this, Fermi level is in the middle. The work function is phi. Work function is phi is obviously equal to chi plus, in this case, Eg by plus Eg by 2. Okay, but there are no electrons at this level, so photoemission cannot take place. There is no density of states. Photoemission cannot take place from there. So the photoemission must take place from wherever there's a high density of electrons available, and that's the valence band. So the threshold energy in this case, Et, is chi plus Eg. Okay. If you take extrinsic semiconductors, it can be pretty easily shown that if you suppose the material is, the important case is if it's highly doped p-type, okay, the Fermi level can be degenerate below the valence band. Okay, and what is Et then? There are holes here, so the field level is, highest field level is there. This is say xi p below the valence band. It's a degenerate semiconductor. Okay, p-type. So there are holes here. Holes mean absence of electrons. So electron emission takes place from here. So Et in this case is equal to chi plus Eg plus xi p. Similarly, for this is for a p-type. For an n-type highly doped semiconductor, you can show that Et, this is p, this is n, will be equal to chi, and n-type semiconductor, so Fermi level is say xi n above the conduction band, so chi minus xi n. Okay. Et will be here. Okay, Et p, Et n will be. However, although this looks attractive that you have reduced the threshold energy, but remember, even for a very heavily doped n-type semiconductor, the concentration of electrons is only 10 to the power 18, 10 to the power 19, etc. Whereas in the valence band, the density of states is 10 to the power 22. So then the question was, how can you reduce this threshold? And since cesium is a material with low work function, if you take a material like gallium arsenide, say it is very heavily doped P plus in the bulk, you coat it with cesium, okay, in a simplified approach, one can say that cesium, being highly easily ionized, can become cesium plus electron. Okay, it can be highly easily ionized. So this Cesium plus gives rise to a sheath of positive charge here. So it is this positive charge which causes the band bending and causes an inversion layer, a strong inversion layer formation at the surface. Right? So as a result, this vacuum level is brought down to the level of the conduction band. So in this case, if you have, say, photons incident in the semiconductor, you can have electron-hole pair creation, and the electron does not have any barrier to overcome. It can diffuse from a distance of almost a micron, the diffusion length. It can just diffuse into vacuum, and hence not only is the efficiency increased, but the range of electrons from the depth of the semiconductor from which the electrons are emitted is also increased, and hence one gets high efficiency, and the threshold of energy is also reduced. Now one can take this a little further and come to this stage where, say for the case of gallium phosphide, band gap is 2.2 eV. Okay, one can have band bending, which is, and chi is only 1.2 eV. So if you have very strong band bending in gallium phosphide, one can get a situation where this is 2.2 electron volts. This is only 1. Okay, band bending is P plus. This is 1.2. So here you have what can be called -1 electron volt. The electron affinity is essentially, so this is what is known as a negative electron affinity photocathode. It turns out that cesium by itself is not very stable, so cesium with oxygen forms a stable surface treatment, which gives you this negative electron affinity. So what happens to the spectral response? The spectral response, it turns out, can be, if this is the energy, we often define the efficiency in terms of yield, that is, number of electrons emitted from the photocathode divided by number of photons per photon. Okay? And obviously 1 is the maximum value. In the case of say gallium arsenide, one gets a emission threshold of about 1.4, and this is way above 0.1. You can get 20-30% yield, and it turns out this threshold has been pushed down to about 1.1 eV. This is gallium arsenide. This is indium arsenide phosphide, negative electron affinity. So 1.1 eV corresponds to 1.1 microns. So we have now photoemitters. These are negative electron affinity photoemitters, which have reasonable yield at about 0.9 or 1 micron. If you compare this with conventional photoemitters, their response will only start at about somewhere here. Conventional multi-alkali S17, etc. The response would only start at somewhere near 2 eV. So this is a major advance in the understanding of photoemission, which has resulted in these negative electron affinity photodiodes. Photo-emitting devices. This, as in the case of optical absorption, one can actually analyze what is this yield as a function of energy, h nu minus, say, some threshold to the power r. Remember, the optical absorption has a behavior something like this, but here we are concerned with the yield, external yield of electrons. And this has been analyzed from the point of view of band structure of semiconductors, and for different direct indirect gap processes, this value of En is different, and En is just the threshold energy Et, and R is also different. It turns out, if I give you just the experimental data, from the point of view of understanding physics of photoemission, it turns out y to the power 1/3 as a function of h nu gives a straight line for gallium arsenide, and this first threshold energy is ET1 is 5.47 eV. This is from emission from the valence band. So one can say that where does the excitation occur from? Excitation from valence band. Okay. Is it indirect or direct? Is there scattering of the electron before they come out, or is there no scattering? Okay. So one can carry out a full-scale analysis exactly as in the case of optical absorption, depending upon the band structure of the material, and get values for the threshold and this R exponent. Okay. For example, this R exponent can be 5/2 or 1 or 2, depending upon the processes involved. What I'm talking about is that, say in general, if you have a semiconductor of this type, you have h nu creating an electron. Okay. This electron can, if it has sufficient energy, it can come out straight without any scattering, or it can undergo collisions, okay, and then come out. Okay. So all these have to be considered in the actual process of photoemission, and this has been analyzed in great detail. The theory is by Kane, and the experimental work was done by Gobelli and Allen at Bell Labs in the early 60s. So the processes are fairly well understood, and this has really resulted in these remarkable NE, negative electron affinity photocathodes. As you see, the highest efficiencies that you can go, the yield can be 1, but as you know, there are devices called photomultipliers, in which you have a tube where the photocathode, the electron is ejected from the photocathode, and you have a series of these are called dinodes, which basically are secondary electron emitters. These dinodes are kept at increasing voltages. Say this is 100, this is 200, etc., etc. If you have a 10 dinode photomultiplier, then you have this maybe at 1000 volts. This is the photocathode, from which the initial electron is emitted, and in each case, each dynode can give you a multiplication of one electron. It results in, say, maybe the ejection of 5 or 10 extra electrons, so you can get a high multiplication factor, even up to 10 to the power 6. Okay, very high sensitivity. Because you can detect single electrons and relatively low noise. Because there is some randomness as to the number of electrons that are emitted, but this is only one type of carrier that is being multiplied, that these are electrons. And one can get reasonably high speed if these devices are properly designed, very high voltages, so the transit time is less. This is obviously not going to be as fast as solid state photodetectors, because some time is required for electron transit. Okay, there will be some delay because of this transit, but if the delay is constant, then it does not add to any signal distortion. So these are vacuum tube photomultipliers, which are extremely important in technology. And one of the aims of solid state devices is to try and develop a solid state photomultiplier which would imitate this and give the same properties and same response. That in this connection, it is the APDs, avalanche photodiodes, which also give rise to gain, can also is highly sensitive, is also fast, which are the analogs of these vacuum tube photomultipliers. However, we'll see that the noise of APDs is higher than the noise of photomultipliers, because of course the random nature of the emission process, and also in the case of APDs we have multiplication of both electrons and holes. Okay, so there's more randomness, and as a result the noise is not as good as photomultipliers. Right, so this in a nutshell is all that I'll discuss regarding photoemissive devices, which are vacuum devices. However, the photocathodes are semiconductors, and that's why I have discussed this topic in some detail. Now, the next type of photodetectors are photoconductive detectors, PC. The broad characteristics have been given in that table. These can be bulk or thin film. There's no junction required. Operating temperature can be 300 down to 4K. You do get gain, and you can get reasonably high speed. You do need a applied voltage. Unlike photovoltaic devices, you need an applied voltage. And noise is generally of two types, as we'll see. So after all, it's a conductor, so there's Johnson noise and there is generation recombination noise. Photoconductive detectors are based on semiconductors, so there is a lambda cutoff, and this depends upon whether the detectors are, if you have an intrinsic type of detector, that means operation, these need not be exactly intrinsic. It can be slightly N-type or slightly P-type, but the emission of electrons is from the valence band to the conduction band. Okay, so the impurity levels are not directly involved, and of course this means that H nu must be equal to or greater than Eg. On the other hand, if you want to go for very long wavelength detectors, then you can have extrinsic detectors in which, suppose you have donor levels here, then in this case H nu must be greater than or equal to Ed. Okay. And since Ed is of the order of 10 millielectron volt, lambda cutoff can be something like say 10 to 12 microns for MCT intrinsic detectors, or they can be 50 microns, okay, for extrinsic detectors, depending upon where the donor or the acceptor levels are. So the two broad classes of detectors. Intrinsic and extrinsic. And how do we compare their performance? Obviously, intrinsic detectors will have a shorter lambda c. Here you have longer lambda c. Since the density of states is much higher in the valence band and in the conduction band, this will have much higher sensitivity. This will have lower detectivity. Okay. Why? Because in this case, the number of electrons that can be emitted depends upon the donor concentration, okay, Nd, which is obviously much less than, say, Nv. Okay. Nd is obviously much less than. So the sensitivity is obviously lower. the other operating requirement is that for an extrinsic detector, these electrons must be in the donor states. Okay, they must not be excited. They must be occupied. They must not be empty. So in order that they be occupied, the temperature must be very low. Okay, so this is very low temperature operation. If you want to go into, so could be something like 4 to 10 degrees K. Whereas these could higher temperature for operation. So the trend is that there are many more extrinsic detectors available, like if you can have germanium doped with copper, germanium doped with gold, you can have silicon doped with gallium, etc. But if you want to have higher detectivity, higher sensitivity, it is better to, if you can try and replace these extrinsic detectors by intrinsic detectors, because the sensitivity would be higher. Obviously, in this case, a crucial consideration is what is ND? What is the heaviest doping that you can do with copper in germanium or gold in germanium? Okay, so the heavier doping that you can make, then obviously the sensitivity will increase. But on the other hand, there are other effects, like if you do very heavy doping, then these levels may merge with the conduction band. Okay, then there will be continuum. So then there will be problems there. Okay, so broadly, a photoconducting detector can be considered to be a slab of material with, say, length L, thickness A, and this dimension, say, B. There's a certain dark current flowing in the absence of light, and depending upon the resistivity of the material and when light is incident, we have an additional current I, pH. Resistance of the sample is just rho L by A into B, and sigma is obviously in NE mu N plus PE mu P is 1 by rho. When sigma dark, and when you have sigma with light, you will have delta N E mu N plus delta P E mu P. And we know that delta N are just given by the generation rate into the life time of electrons. Delta P is generation rate into the lifetime of holes. And so we can show that the gain, which is the number of electrons crossing between electrodes, over the number of photons incident, is tau n by Tn plus tau p by Tp, where Tn and tau p are the transit times, and you can, from simple, if the mobility is mu, applied voltage is V, the transit times are L squared by mu n V and L squared by mu PV. Essentially here, the gain can be large if the transit times are small compared with the lifetimes. And in that case, what we are having is that when an electron exits, if tau n is much larger than Tn, when an electron exits at an electrode, then another electron is injected, and that keeps on circulating until the recombination time is reached, and that is the reason why gain is possible in a photoconductor.